Liquid-tight conduit without a metal sheath is commonly known as Carflex, regardless of the spelling. It is a flexible, non-metallic conduit used to protect wires from moisture, dust, and abrasion. The National Electrical Code, referred to as NEC, does not prohibit the use of Carflex for 480-volt branch circuits. However, concerns about physical damage and the potential for arcing fault should be considered. For the given scenario, where the Carflex is used for a 480-volt branch circuit that penetrates the roof decking into the air conditioning unit, the following considerations apply. Firstly, a bushing is not required for the penetration of the roof decking, as the plastic sheath of the Carflex provides adequate protection against damage. Secondly, conductors should not be installed free air inside the air conditioning unit. A raceway or conduit must be used to protect the conductors from contact with other conductors or surfaces. To enhance safety and meet code requirements, the following changes are recommended. Firstly, instead of Carflex, an armored cable, often called BX, or metal conduit such as electrical metallic tubing referred to as EMT or rigid metal conduit referred to as RMC would provide better protection against physical damage and arcing faults. Secondly, at the point where the metal conduit or armored cable enters the air conditioning unit, a junction box should be installed to provide additional protection and a convenient point for termination. While Carflex can be used for 480-volt branch circuits in certain situations, it is not the ideal choice due to concerns about physical damage. In the given scenario, it is recommended to use an armored cable or metal conduit and to install a junction box at the point of entry into the air conditioning unit. Considering the use of Carflex in electrical installations, several key aspects should be carefully evaluated. Firstly, the environment where the conduit is installed is crucial. Carflex is suitable for locations where flexibility is needed and where the conduit is protected from significant physical damage. However, in areas prone to impacts, abrasion, or other forms of mechanical stress, more robust conduit types such as EMT or RMC are preferable. Secondly, the voltage of the circuit being protected is a significant factor. While the NEC permits the use of Carflex for 480-volt circuits, it is essential to ensure that the conduit is properly installed and supported to prevent potential failures. The higher the voltage, the greater the risk of arcing faults if the insulation is compromised. Thirdly, proper grounding and bonding are essential for electrical safety. When using Carflex, ensure that the grounding conductor is adequately sized and properly connected to all metallic enclosures and equipment. This helps to minimize the risk of electric shock and provides a low impedance path for fault currents to flow back to the source, facilitating the operation of overcurrent protective devices. Fourthly, consider the specific requirements of the equipment being connected. For example, air conditioning units often have specific requirements for the type of conduit and wiring methods that can be used. Always consult the manufacturer's instructions and local electrical codes to ensure compliance. Fifthly, when transitioning from EMT or RMC to Carflex, use appropriate fittings and connectors to maintain the integrity of the raceway system. These fittings should be listed for the purpose and properly installed to provide a secure and watertight connection. Transitioning from a metallic conduit system to Carflex requires careful attention to detail to ensure electrical safety and code compliance. Here's a detailed breakdown of the key considerations and steps involved. Firstly, select the appropriate fittings. Use fittings specifically designed for transitioning from EMT or RMC to liquid-tight flexible metal or non-metallic conduit. These fittings typically consist of a connector that threads onto the end of the EMT or RMC and a separate connector that clamps onto the Carflex. Ensure that the fittings are listed for the specific types and sizes of conduits being used. Secondly, prepare the EMT or RMC. Cut the EMT or RMC to the desired length using a pipe cutter or hacksaw. Deburr the cut end to remove any sharp edges or burrs that could damage the wires or cables. Clean the end of the conduit to remove any dirt, oil, or other contaminants. Thirdly, install the EMT or RMC connector. Thread the appropriate connector onto the end of the EMT or RMC. Tighten the connector securely using a wrench or pliers. Ensure that the connector is properly grounded and bonded to the conduit. Fourthly, prepare the Carflex. Cut the Carflex to the desired length using a utility knife or conduit cutter. Be careful not to damage the wires or cables inside the conduit. Remove any sharp edges or burrs from the cut end of the Carflex. Fifthly, install the Carflex connector. Insert the Carflex into the appropriate connector. Tighten the connector securely using a wrench or pliers. Ensure that the connector is properly seated and that the Carflex is securely clamped in place. Sixthly, pull the wires or cables. Carefully pull the wires or cables through the ENT or RMC, the transition fitting, and the Carflex. Avoid pulling the wires or cables too tightly, as this could damage them. Ensure that the wires or cables are properly supported and secured throughout the raceway system. Seventhly, inspect the installation. Inspect the installation to ensure that all fittings are properly installed and tightened. Check for any signs of damage or wear to the conduits, fittings, or wires or cables. Verify that the grounding and bonding connections are secure and properly made. Eighthly, test the installation. Test the installation to ensure that it is working properly. Use a multimeter or other testing device to verify that the wires or cables are properly connected and that there are no shorts or ground faults. Ensure that the equipment being powered by the circuit is functioning correctly. Regularly inspect to maintain the transition to ensure its continued safety and reliability. Check for any signs of wear or damage to the conduit, fittings, or wires or cables. Retighten any loose connections, then replace any damaged components promptly. Good workmanship and attention to detail are essential for creating a safe and reliable electrical installation. Using the wrong type of conduit in an electrical installation can lead to a variety of problems, ranging from minor inconveniences to serious safety hazards. Firstly, physical damage. Different types of conduit offer varying levels of protection against physical damage. Using a conduit that is not robust enough for the environment in which it is installed can result in damage to the wires or cables inside, leading to shorts, ground faults, or even fires. Secondly, moisture ingress. Some types of conduit are not watertight and can allow moisture to enter the raceway system. This can lead to corrosion of the wires or cables, as well as damage to electrical equipment. Thirdly, electrical shock. Using the wrong type of conduit can compromise the grounding and bonding of the electrical system, increasing the risk of electrical shock. This is particularly important in wet or damp locations, where the risk of shock is higher. Fourthly, code violations. Using the wrong type of conduit can result in violations of the NEC or other applicable electrical codes. This can lead to fines, penalties, and even the shutdown of the electrical system. Fifthly, premature failure. Using the wrong type of conduit can shorten the lifespan of the electrical system. This can lead to increased maintenance costs and the need for premature replacement of the conduit and wiring. Proper selection and installation of electrical conduit are essential for ensuring the safety and reliability of electrical systems. Factors to consider when selecting conduit include the environment, the voltage of the circuit, the type of wiring, and the applicable electrical codes. When installing conduit, it is important to follow the manufacturer's instructions and to use the correct fittings and connectors. Here's a more in-depth explanation of each of the points above. Firstly, physical damage resistance. Different types of conduit offer varying degrees of resistance to physical damage. For example, RMC is the most durable type of conduit and is suitable for use in areas where it is likely to be subjected to severe impacts or abrasion. EMT is less durable than RMC but is still suitable for use in many applications. Carflex is the least durable type of conduit and is only suitable for use in areas where it is protected from physical damage. Secondly, moisture resistance. Some types of conduit are watertight, while others are not. RMC and PVC conduit are both watertight and are suitable for use in wet or damp locations. ENT is not watertight and should not be used in wet or damp locations unless it is specifically listed for that purpose. Thirdly, grounding and bonding. Proper grounding and bonding are essential for electrical safety. All metallic conduit systems must be properly grounded and bonded to ensure that there is a low impedance path for fault currents to flow back to the source. This helps to protect people from electrical shock and prevents damage to electrical equipment. Fourthly, code compliance. The NEC and other applicable electrical codes specify the types of conduit that can be used in different applications. It is important to comply with these codes to ensure the safety of the electrical system. Fifthly, lifespan. The lifespan of an electrical conduit system depends on the type of conduit used, the environment in which it is installed, and the quality of the installation. RMC is the most durable type of conduit and can last for many years. EMT is less durable than RMC but can still last for a long time if it is properly installed and maintained. Carflex is the least durable type of conduit and may need to be replaced more frequently. When selecting electrical conduit, it is important to consider all of these factors. By choosing the right type of conduit for the application, you can ensure the safety and reliability of the electrical system. The proper support of electrical conduit is a critical aspect of electrical installations, ensuring both safety and compliance with the NEC. Adequate support prevents strain on the conduit, protects the enclosed conductors, and maintains the integrity of the electrical system. Here's a detailed guide on how to properly support electrical conduit. Firstly, understand code requirements. The NEC provides specific guidelines for supporting different types of conduit. Article 344 covers the requirements for rigid metal conduit, Article 348 for EMT, and Article 356 for liquid-tight flexible metal conduit, among others. These articles specify the maximum distances between supports and the methods of support. Secondly, choose the right support hardware. Select support hardware that is appropriate for the type and size of conduit being installed. Common support hardware includes conduit clamps, straps, hangers, and standoffs. Ensure that the hardware is listed for electrical use and is made of materials compatible with the conduit to prevent corrosion. Thirdly, spacing requirements. The spacing between conduit supports depends on the type and size of the conduit. For example, EMT typically requires support every 10 feet, while rigid metal conduit may be supported at longer intervals. Consult the NEC for specific spacing requirements for each type of conduit. Fourthly, secure the supports properly. Attach the conduit supports securely to the building structure using appropriate fasteners. For concrete or masonry walls, use expansion anchors or concrete screws. For wood framing, use wood screws or lag bolts. Ensure that the supports are aligned properly to prevent strain on the conduit. Fifthly, support at terminations and bends. Provide support within 3 feet of conduit terminations, such as at junction boxes or equipment enclosures. This prevents strain on the conduit connectors and ensures a secure connection. For conduit runs with bends, support the conduit within 3 feet of each bend to prevent the conduit from shifting or sagging. Sixthly, expansion and contraction. In areas with significant temperature variations, consider the effects of expansion and contraction on the conduit. Use expansion couplings or expansion fittings to allow for movement without putting stress on the conduit or supports. Seventhly, avoid over-tightening. When installing conduit clamps and straps, avoid over-tightening the fasteners. Over-tightening can damage the conduit or the support hardware. Tighten the fasteners just enough to secure the conduit without crushing it. Eighthly, inspect the installation. After installing the conduit and supports, inspect the installation to ensure that everything is properly secured and aligned. Check for any signs of strain or damage to the conduit or supports. Make any necessary adjustments to ensure that the installation meets code requirements and is safe and reliable. When working with electrical conduit, safety should always be a top priority. Firstly, to energize the circuit. Before starting any work on electrical conduit, always to energize the circuit at the main breaker or disconnect switch. This will prevent the risk of electric shock. Secondly, wear appropriate personal protective equipment. Wear safety glasses, gloves, and other appropriate personal protective equipment to protect yourself from hazards such as flying debris, sharp edges, and electrical shock. Thirdly, use the right tools. Use the right tools for the job, such as conduit benders, cutters, and threaders. Make sure that the tools are in good condition and are properly maintained. Fourthly, work in a well-ventilated area. When cutting or threading conduit, work in a well-ventilated area to avoid inhaling harmful fumes or dust. Fifthly, avoid working in wet conditions. Avoid working on electrical conduit in wet conditions, as this can increase the risk of electric shock. Sixthly, follow code requirement. Follow all applicable electrical codes and regulations when installing or working on electrical conduit. Seventhly, inspect the work. After completing the work, inspect the installation to ensure that it is safe and meets code requirements. Eighthly, test the circuit. After completing the work and inspecting the installation, test the circuit to ensure that it is working properly. The selection of appropriate fittings for electrical conduit is crucial for ensuring the safety, reliability, and longevity of electrical systems. Different types of conduit require specific fittings to maintain a secure and code-compliant installation. Here's a detailed overview of selecting the right fittings for various conduit types. Firstly, rigid metal conduit RMC. RMC fittings are designed to provide a robust, watertight connection. Common fittings include couplings for joining two sections of conduit, elbows for changing direction, and connectors for attaching the conduit to boxes or enclosures. These fittings are typically threaded and made of galvanized steel or aluminum. When selecting RMC fittings, ensure that they are listed for use with rigid metal conduit and that they are properly sized for the conduit being used. Secondly, electrical metallic tubing EMT. EMT fittings are used to connect sections of EMT and to attach the conduit to boxes or enclosures. Common fittings include compression connectors, set screw connectors, and couplings. Compression connectors provide a watertight seal, while set screw connectors are a more economical option. EMT fittings are typically made of galvanized steel or aluminum. When selecting EMT fittings, ensure that they are listed for use with EMT and that they are properly sized for the conduit being used. Thirdly, flexible metal conduit FMC. FMC fittings are designed to provide a flexible yet secure connection. Common fittings include squeeze connectors and set screw connectors. Squeeze connectors provide a watertight seal, while set screw connectors are a more economical option. FMC fittings are typically made of galvanized steel or aluminum. When selecting FMC fittings, ensure that they are listed for use with FMC and that they are properly sized for the conduit being used. Fourthly, liquid-tight flexible metal conduit LFMC. LFMC fittings are designed to provide a watertight flexible connection. Common fittings include straight connectors, 45-degree connectors, and 90-degree connectors. These fittings typically have a rubber or plastic seal to prevent moisture from entering the conduit. LFMC fittings are typically made of galvanized steel or aluminum with a plastic coating. When selecting LFMC fittings, ensure that they are listed for use with LFMC and that they are properly sized for the conduit being used. Fifthly, polyvinyl chloride PVC conduit. PVC fittings are used to connect sections of PVC conduit and to attach the conduit to boxes or enclosures. Common fittings include couplings, elbows, and connectors. These fittings are typically glued together using PVC cement. PVC fittings are made of PVC plastic. When selecting PVC fittings, ensure that they are listed for use with PVC conduit and that they are properly sized for the conduit being used. Always consult the NEC and local electrical codes to ensure compliance with all applicable regulations. The NEC provides detailed requirements for the types of fittings that can be used with different types of conduit. Also, use only listed fittings. Listed fittings have been tested and certified by a recognized testing laboratory, such as Underwriters Laboratories, or UL. This ensures that the fittings meet applicable safety standards and are suitable for use in electrical installations. The NEC is a comprehensive set of standards that governs the safe installation of electrical wiring and equipment. It is updated every 3 years to reflect changes in technology and best practices. Understanding the NEC is essential for anyone who works with electricity, including electricians, engineers, and inspectors. The NEC is organized into chapters, articles, and sections. Each chapter covers a specific topic, such as wiring methods, equipment, or special occupancies. Each article provides more detailed requirements for a particular aspect of the topic. Each section provides specific rules for a particular situation. The NEC is not a law, but it is widely adopted by state and local governments. In many jurisdictions, electrical installations must comply with the NEC in order to be approved. The NEC is a complex document, but it is essential for ensuring the safety of electrical installations. Here are some key concepts from the NEC. Firstly, overcurrent protection. Overcurrent protection devices, such as circuit breakers and fuses, are used to protect electrical circuits from overloads and short circuits. The NEC specifies the types and sizes of overcurrent protection devices that must be used in different situations. Secondly, grounding and bonding. Grounding and bonding are used to provide a safe path for fault currents to flow back to the source. This helps to protect people from electric shock and prevents damage to electrical equipment. The NEC specifies the methods and materials that must be used for grounding and bonding. Thirdly, wiring methods. The NEC specifies the types of wiring methods that can be used in different situations. Wiring methods include conduit, cable, and open wiring. The NEC also specifies the requirements for installing and supporting wiring. Fourthly, equipment. The NEC specifies the requirements for electrical equipment such as switches, receptacles, and lighting fixtures. The NEC also specifies the requirements for installing and using electrical equipment. Fifthly, special occupancies. The NEC provides special requirements for electrical installations and special occupancies such as hospitals, schools, and hazardous locations. Understanding the NEC is essential for ensuring the safety of electrical installations. By following the NEC, you can help to protect people from electric shock and prevent damage to electrical equipment. When it comes to electrical safety, there are several key considerations that should always be kept in mind. Firstly, always to energize circuits before working on them. This is the most important safety precaution you can take. Before starting any work on an electrical circuit, always turn off the power at the main breaker or disconnect switch. Secondly, use the right tools for the job. Using the wrong tools can damage electrical equipment and increase the risk of electric shock. Always use tools that are designed for the specific task you are performing. Thirdly, wear appropriate personal protective equipment. Personal protective equipment such as safety glasses, gloves, and insulated shoes can help to protect you from electrical shock and other hazards. Fourthly, inspect electrical equipment regularly. Inspect electrical equipment regularly for signs of damage or wear. Replace any damaged or worn equipment immediately. Fifthly, never overload circuits. Overloading circuits can cause them to overheat and potentially start a fire. Never plug too many appliances or devices into a single circuit. Sixthly, be aware of wet conditions. Water is a conductor of electricity. Avoid working on electrical equipment in wet conditions. Seventhly, follow code requirements. Follow all applicable electrical codes and regulations when installing or working on electrical equipment. Eighthly, get help from a qualified electrician. If you are not comfortable working on electrical equipment, get help from a qualified electrician. The purpose of a junction box in electrical wiring is multifaceted, serving several critical functions to ensure safety and facilitate maintenance and modifications. Firstly, providing a safe enclosure for wire connections. Junction boxes are designed to enclose and protect electrical connections from the environment and accidental contact. This is crucial because exposed connections can pose a significant risk of electric shock or fire. The box is typically made of metal or durable plastic that is non-conductive, providing a barrier between the electrical connections and the surrounding environment. Secondly, facilitating wire splicing and termination. Junction boxes offer a designated space for splicing wires together or terminating them. This is particularly useful when extending circuits, branching off to power new devices, or replacing damaged sections of wiring. The connections inside the box should be made using approved methods such as wire connectors, also known as wire nuts, terminal strips, or crimped connections. Thirdly, complying with electrical codes and regulations. Electrical codes, such as the NEC, mandate the use of junction boxes for all wire splices and terminations. These codes specify the types of boxes that can be used in different locations, the methods for securing them, and the requirements for grounding and bonding. Compliance with these codes is essential for ensuring the safety and legality of electrical installations. Fourthly, providing access for maintenance and troubleshooting. Junction boxes allow easy access to the wire connections for inspection, testing, and repair. This is particularly important for troubleshooting electrical problems or making modifications to the wiring system. The cover of the junction box can be easily removed to access the connections inside. Fifthly, protecting wires from physical damage. Junction boxes provide a physical barrier that protects wires from damage caused by impacts, abrasion, or other forms of mechanical stress. This is particularly important in areas where the wires are exposed or vulnerable to damage. Sixthly, preventing the spread of fire. Metal junction boxes can help to contain a fire within the box, preventing it from spreading to other parts of the building. This is because metal is non-combustible and can withstand high temperatures. Overall, the purpose of a junction box is to provide a safe, accessible, and code-compliant enclosure for electrical connections. By using junction boxes, you can help to ensure the safety, reliability, and longevity of electrical systems. When installing a junction box, there are several key considerations to keep in mind. Firstly, box fill calculations. The NEC specifies the maximum number of wires, devices, and fittings that can be installed in a junction box. This is known as the box fill calculation. The purpose of the box fill calculation is to prevent overcrowding of the box, which can lead to overheating and other safety hazards. Secondly, grounding and bonding. All metal junction boxes must be properly grounded and bonded to ensure that there is a low impedance path for fault currents to flow back to the source. This helps to protect people from electric shock and prevents damage to electrical equipment. Thirdly, location. The location of the junction box should be carefully considered. The box should be installed in a location that is easily accessible for maintenance and troubleshooting. It should also be protected from physical damage and moisture. Fourthly, securing the box. The junction box must be securely mounted to a structural member of the building. This can be done using screws, bolts, or other appropriate fasteners. Fifthly, wire connectors. The wire connectors used in the junction box must be of the correct type and size for the wires being connected. They must also be properly installed to ensure a secure and reliable connection. Remember, electrical work can be dangerous. If you are not comfortable working with electricity, get help from a qualified electrician.